Assalamu alaikum. This is lecture 9 of data security and encryption, and in this lecture we are going to talk about data encryption standards. In this lecture I am going to illustrate the principles of modern symmetric ciphers. For this purpose we have to focus on mostly used symmetric ciphers. The mostly used symmetric cipher is known as the Data Encryption Standard, known as DES. Although numerous symmetric ciphers have been developed since the introduction of Data Encryption Standard, and although it is destined to be replaced by the Advanced Encryption Standard known as AES, DES still remains the most important algorithm. Furthermore, study of data encryption standard provides an understanding of the principles used in the symmetric ciphers. The structure of data encryption standard and most symmetric ciphers is very complex and it cannot be explained or solved using the hand-generated practices. Let's have a look at the lecture contents, and in this lecture we are going to study about the data encryption standard, and we will discuss the process of encryption and the decryption in DES. Then we are going to discuss an example and study the effect called Avalanche Effect. There will be some discussion about the strengths of data encryption standards by using different keys such as 56-bit keys or 64-bit keys, or using a more secure key such as using a triple data encryption standard. We will briefly discuss about the timing attacks, and then we will discuss about block cipher design principles. The three main principles of block cipher designs are number of the rounds. As we discussed in the previous lecture, we have a design function and we can actually uh, specify different design functions to specify the strength of our design uh, algorithm. And then there is a concept called key schedule algorithm, which will be discussed later part of the chapter. So at the end of this lecture you should be able to present an overview of the data encryption standard, the most widely used algorithm in the data security and encryption. And you should be able to explain the concepts of avalanche effect, and you should be able to discuss the strengths of data encryption standards, and finally you should summarize the principal block cipher design principles. Over the years, data encryption standard has been a dominant symmetric encryption algorithm. Especially, it has been used widely in the financial applications. In 1994, the data encryption standard was extended for 5 years use in most of the critical applications. However, in 1999, a new version was issued known as triple data encryption standard, which was actually a repetition of data encryption standards with using different keys and replicating the steps 3 times to actually enhance the security. The underlying encryption and decryption algorithm was the same for data encryption standard and the triple data encryption standard. It still remains an important data encryption cipher, and it is very much useful to understand its principles. So if we look at the history of data encryption standard, it was issued in 1977 by National Bureau of Standards, known as National Institute of Standards for Technology, as Federal Information Processing Standard. and it was most widely used encryption scheme until the introduction of Advanced Encryption Standard, which was introduced in 2001. Algorithm itself is referred as data encryption algorithm, and data are encrypted in 64-bit blocks using a 56-bit keys. The algorithm transforms the 64-bit input in a series of steps into a 64-bit output. That means the size of the block remains same, and it is very important to recall that it is a block cipher algorithm and it is different from the stream cipher algorithm. Another important step to recall that the same steps are used with the same key to reverse the encryption that is used in the decryption. So the overall scheme of data encryption is depicted in this diagram. There are two inputs to the encryption function. The number one input is the plain text and the other input is the key to the encryption algorithm. In the case, the plain text must be 64 bits in the length and the key is 56 bits in the length. So the processing of plain text actually proceeds in three phases. First of all, the input is fed to a permutation algorithm known as initial permutation. So it rearranges the bits to produce the permuted input. So this is followed by the phase consisting of 16 rounds. These rounds are similar to the crystal cipher which we discussed in the last lecture. So these rounds involve both permutation and the substitution functions. The output of last, usually the 16 round, consists of 64 bits that are a function of input plain text and the key. So the left and the right halves of the inputs are swapped to produce the pre-output, and finally the permutation is performed in the reverse order that it was performed in the initial step to produce the actual 64-bit cipher text. With the exception of initial and final permutation, the DES is the exact structure of the crystal cipher discussed in the last lecture. If you look at the right hand side of the image, it shows the way that which a 56-bit key is used. Initially, a key is passed through a permutation function much similar to the plain text permutation. Then for each round in the 16 rounds, a sub-key is produced with a combination of a left circular shift and a permutation. The permutation function is same for each round, but a different sub-key is produced because of the repeated shift on the key bits. So you take the initial key of 64-bit and perform a permutation function and change the key to pick the 56 bits, and then you, for each round, you perform a left circular shift and you produce another key of 48 bits and use this key to change the input in each round and produce an output after 16 rounds, and then perform a swapping operation from the left to right uh, half of the input, and then perform the reverse of initial permutation and generate the 64-bit cipher. Similarly, when you want to decrypt, it is the same process but done in the a reverse order. Similarly, if you want to perform the decryption of 64-bit cipher, you start the same process and you perform the 32-bit swap, and then you perform the 16 steps in the reverse order. The keys are also reversed, and finally the permutation will resolve to the original 64-bit plain text. So let's have a look at the example and consider some of its implications. Although it is very difficult to produce these results of the examples by hand, you will find it very informative to study the pattern that occurs from one step to the next. For example, the plain text is a hexadecimal palindrome, and the plain text key is depicted as here. So after the initial round of input permutation, we get two hops of input known as left and right. This is actually the permuted uh, value of initial plain text. And we have a key represented here, and at each round key is permutated and used with the left shift. And after each round the left and the right half of the input is shown here. So after 16 rounds the input is formulated as a ciphertext, and the final round of input permutation in the reverse order of first step is performed to actually produce a final ciphertext, which is represented in the last step. So a very important and desirable property of any encryption algorithm is that a small change in the either of the plaintext or the key should produce a significant change in the ciphertext. In particular, a change in the one bit of the plaintext or one bit of the key should produce a change in many bits of the ciphertext. This is referred as avalanche effect. That means if you change one bit or multiple bits in the key or the input you perform input permutation, there will be change in the ciphertext. If the change is very small, this might provide a way to reduce the size of plain text or key space to be searched. So this image shows the result when the fourth bit of plain text is changed. You can observe the first value of hex that was changed from 0 to 1. So this means the first 4 bits or the fourth bit is changed for the plain text. The second column of the table shows the intermediate 64-bit values. For example, if you change one bit, the value changes from this to this value. The third column shows the number of bits that differ between the two intermediate values. So in this case, the difference between these two values is 1 bit. Similarly, if you look at the next step, only 1 bit is shifted or permutated. So again the difference of value is 1. So the table shows that after just 3 rounds of uh, permutations, 18 bits differ from two respective values. So on completion, two ciphertexts differ in 32 bits as depicted in the example diagram. Similarly, this table or image shows change in the key specifying the avalanche effect in the data encryption standard. So a similar test is performed here using the original plain text with the two keys that differ in only the fourth bit position. So again, the result shows that about half of the bits in the ciphertext differ, that avalanche effect is pronounced after just a few rounds. For example, if you can see, after one round, 3 bits are different from each of the input, and after second it is 11, and then it reaches to the 25. So since its adoption as a federal standard, there has been many concerns about the level of security provided by data encryption standards. So there are two main concerns at large. The number one is key size, and the number two is the nature of algorithm. So this table actually represents the use of key size and average required uh, time for exhaustive key search in any encrypted value. So this represents a different uh, value of key size in bits, and this actually shows the technology used to cipher and value, and this provides the number of alternate keys, and this requires, these two columns require the time to actually decrypt the value. So with a key length of 56 bits, it is particularly used in the data encryption standard. Possible keys, which is approximately 7.2 cross 10 raised to power 16 keys. So assuming that on average half of the key space is to be searched, a single machine performing one data encryption per microsecond will take 1,000 years to break the cipher. However, computation power has increased, and the assumption of one encryption per second is not very much applicable these days. As it was presented in 1977, the technology existed to build a parallel machine with 1 million encryption devices in parallel, and each performing one encryption per microsecond. So if we assume such kind of system will exist, this will bring the average search time down to 10 hours from a very large value. So the authors estimated that the cost would be about 20 million in 1977. However, with the current technology, it is not even necessary to use a special purpose hardware. So speed of commercial processors is very much high these days, and it can actually break the security of data encryption standard. The Seagate technology, a famous or renowned organization developing for data and implementing data encryption standards, suggests that a rate of 1 billion key combinations per second is reasonable for today's multi-core computers. So both Intel and AMD now offer hardware-based instructions to accelerate the use of advanced encryption standards. So test runs on the multi-core Intel machines resulted in an encryption rate of about half a billion encryption per second. So you can recent another example says that there are 10 raised to power 13 encryption that can be done per second. So with these results in mind, this table shows that how much time is required for the brute force attack to find out the various keys. So as it can be seen, single PC can break the data encryption standard in about a year. So if multiple PCs are used, In parallel, the time is drastically shortened, and today's supercomputer would be able to find a key about an 1 hour that was implemented using the 56-bit key and using the data encryption standard. Similarly, advanced encryption standard uses 128-bit keys by default, and it have 10 raised to power 38 bits, and normal computer would require 10 raised to power 21 years. However, a supercomputer can decode this in 10 raised to power 17 years, which is a very long time, and advanced encryption standard is unbreakable. So even if we manage the speed of the attacking by attacker by factor of 1 trillion, it would still take over 1,000 years to break the code using 128-bit encryption standard using the advanced encryption standard. Similarly, as we discussed, triple DES uses the triple effect of 56-bit keys, and it uses the 168-bit keys, and there is 10 is power 50 possible keys, and 10 is power 33 years if you have 10 is power 9 decryption per second, and 10 is power 36 years if you have 10 is power 13 decryptions per second. Advanced encryption standard also uses 192 bits and 256 bits of encryption respectively. So this will also enhance the number of years for decryption of cipher text. Another strength of data encryption standard is referred as timing attack. So we will discuss the timing attacks in more details in the next lectures as they relate to public key algorithms. However, the issue may also be relevant to symmetric ciphers somewhat. Timing attacks are the one in which information about the key or the ciphertext is obtained by observing how long it takes for a given implementation to perform the decryption on the various ciphertext, which is very a vague actually concept to find out the uh, actual strength of data encryption standard, because just by observing the time taken to implement to perform a decryption and encryption, it is very difficult to analyze the keys or obtain the keys. So timing attacks exploit the fact that the encryption or decryption algorithm often takes slightly different amount of time on different inputs. However, so far it is appeared unlikely that this technique will ever be successful against data encryption standard or more powerful symmetric ciphers such as triple data encryption standard or advanced encryption standards. Much progress has been made in designing block ciphers that are very strong. However, the basic principles that have been employed in 1970s are still the same. So in this section, we are going to look at three critical aspects of block cipher design. These three aspects are the number of rounds, design of the function f, and the key scheduling. So first, let's look at the first choice, the number of rounds. So it states that if you have greater the number of rounds, the more difficult it is to perform cryptanalysis on your system. It is applicable even if you have a relatively weak function f. So in general, the criterion should be that the number of rounds is chosen so that the non-cryptanalytic efforts require greater effort than the simple brute force key search attack. So this criterion was certainly used in the design of data encryption standard. So if data encryption standard had 15 or fewer rounds, a differential cryptanalysis would require less effort than a brute force key search attack. A differential attack is different than the brute force attack, and it requires more combination than a brute force attack to actually compromise the security. But if you use 15 or less rounds, the differential attack is more likely to happen than a brute force attack. So this criterion is very attractive because it allows you to judge the strength of your algorithm, and you can compare different algorithms based on this criteria. The strength of any algorithm that satisfies this criterion can be judged solely on the key length. The second most important block cipher design principle is design of function f. So it is the heart of crystal block cipher, and it provides the element of confusion in your crystal block cipher. Thus, it must be difficult to unscramble the substitution performed by this function, and one obvious criterion is that f must be nonlinear. To state that if your f function is more nonlinear, then it will be more difficult to perform the cryptanalysis. So in rough terms, the more difficult to approximate your function f by set of linear equation, so your function will be non-linear. Several other criteria should be considered in designing your function f. We would like the algorithm to have the good avalanche properties. So if you recall that in general terms that a change, as we discussed in the last few slides, that a change in one bit of the input should produce change in many bits of output. So one of the stringent version of this is called strict avalanche criterion, known as SAC. So it states that if you change any of the output bit j of any S box side, so it states that any output bit j of any S box should change with the probability of 1 by 2 when any single input bit I is inverted for all ij. So it is similar to the last explanation that if you change your input bit, any of input bit, your output bit j will change. So it will have 1 by 2 property. That means there is 50% chance that your output bit will be changed. Another criterion proposed was the bit independence criteria. It states that the output bit j and k should change independently when any of single input I is inverted for all I, j, k. It is also discussed in the last implementation of data encryption standard. When you change any amount of bits such as I, there is a probability that I, j, k, all of the inputs will be changed. So these two criteria appear to strengthen the effectiveness of the confusion function. Final block cipher design principle is key schedule algorithm. So with any Feistel block cipher, the key is used to generate one subkey for each round. In general, we would like to select subkeys to maximize the difficulty of reducing individual subkeys and the difficulty of working back to the main key. It is suggested that at minimum the key should guarantee the key or ciphertext both criteria, strict avalanche criteria and bit independent criteria. However, no general principle for this have been yet achieved. So that leads us to the conclusion of this lecture. In this lecture, we discussed a data encryption standard, and we looked at the encryption and decryption process of this standard, and we studied the avalanche effect that stated that if you change or permute the one input bit or number of input bits, there is more chance that the output bits will be changed after each round. Then we discussed the strength of data encryption standard, that how long it can take for a cryptanalytic attack to actually decrypt the information or find out the keys. So we saw there number of algorithms use different kind of keys, and with different kind of processing power, there is a huge amount of time required to decrypt the keys. So with 56-bit keys, a supercomputer can break your code in 1 hour. However, if you use a much larger key such as 128 bits or 168 bits, your system is more likely to be secure, and even a supercomputer will not be able to decrypt your information. Then we briefly discussed about the timing attacks, and it are very difficult to generate a timing attack and to extract the information. And finally, we overview the block cipher design principle, that how the components actually enhance the security or the performance of your encryption algorithm. So three important elements were number of the rounds. That means if you increase the number of rounds, your system will be more secure. And if you have a more complex or non-linear design function F, your system integrity or security will increase. Similarly, if you use a key schedule algorithm that hinders or that hinders the actual uh, generation of keys, or that uh, actually emphasizes the use of avalanche effect or bit independence criteria. If you want to study more, you can read the chapter 4 of the recommended book. You can ask me using any of the designated medium, or you can conduct the answer session, question and answer session at Microsoft Teams. Thank you very much.